Hi everyone, since our school days we are told that electron in an atom revolves around the nucleus, and similarly the moon revolves around the earth. So here I am showing a picture where electron is revolving around this nucleus. As we know, nucleus is positively charged and electron is negatively charged. Now we also know that this electron being negatively charged will be attracted by this positively charged nucleus, right? And this force of attraction is what we call the electrostatic force. Similarly, from Newton's law of gravitation, we know that this moon is gravitationally attracted by the earth. So this force represents the gravitational force on moon by earth, and this force represents the electrostatic force on electron by the nucleus. Now a very popular question is, if there is a force of attraction, why is this electron not falling into the nucleus? Or in this case, why the moon is not falling onto the earth? And the answer to this, you may be surprised, is actually the moon is falling and even the electron is falling. The moon is falling towards earth and electron is falling towards nucleus. Now you may be thinking that if moon is actually falling towards earth, by now it should have reached earth, isn't it? So am I really right when I say the moon is falling towards earth and even electron is falling towards nucleus? Let us try to understand. Let us first understand, what does a force actually do? For that, let us use the famous Newton's second law of motion, which says the total force, this F represents the total force acting on a body whose mass is m, and A is the acceleration produced in the body. Now the definition of acceleration is change in velocity divided by the time it took for the velocity to change. So what this equation says? This equation says if you apply some force, then it results in acceleration, which in turn produces a change in velocity. Therefore, if a body is at rest, then what is its velocity? Right now, 0. So if you apply force on this body, then what will happen? This body will start moving. So it may move with some velocity, let's assume 5 meters per second. So you can see, due to the application of this force, what happened? Its velocity changed. From rest, it started moving, right? What happens if you apply force on a body which is already moving? So let's say this body is moving this side with velocity 5 meters per second. And now what I do, I apply force on this body in the same direction as its motion. Then I hope all of you will agree that this body will now start moving faster because of this force. So it may start moving with a velocity which could be 8 meters per second, right? So due to the force, again you can see its velocity has changed. What if I apply force in the opposite direction, not in the same direction as velocity, but in opposite direction? Then what will happen? Well, the body will slow down and therefore its velocity will reduce. Because the body will slow down, its velocity may become something like 2 meters per second. So in all these examples, you must have seen that the force is responsible to change the velocity of the body, right? Now imagine this body is moving with some velocity. Now instead of applying force in the same direction or in the opposite direction, what if I apply force in a perpendicular direction? Then what do you think will happen? Well, now the body's direction of motion, what? Direction of motion will change. So this body will start moving something like this. To see an example of this, take a body and throw it horizontally. Will it continue straight? No, because there is a force of gravity which acts right now perpendicular to its motion, right? So this force will turn the body, as you all know, right? Let us now do a thought experiment where you have to imagine there is an apple on a tree, and when the apple is ripe, what will happen? It will fall down, isn't it? Now imagine if the tree was slightly taller, not of the same height but slightly taller. Then if I ask, will this apple which is slightly taller than this, will this apple fall when it is ripe? What do you think? Well, the answer is yes. Even this apple will fall and even this apple will fall, right? What if the tree was slightly taller? Will this apple fall when it is ripe? Obviously, yes sir, it will fall. So this way, if you keep making the tree taller and taller, every time what you will be saying? The apple will fall, the apple will fall, the apple will fall, right? Now imagine, as you kept increasing the height of the apple, you have reached the height of the moon. So now, this apple, which is at the same height as the moon, is it going to fall or not? Remember, till now you were saying it will fall. So obviously now also you have to say the apple will fall. So this apple has to fall towards earth, right? But we all know moon is not falling straight towards earth. Why is it so? The difference between this apple and moon is when this apple started, remember it was at rest. So just like this marker, if you leave it from rest, it will fall straight towards earth, right? But this moon is not at rest. It already has a motion, right? So the moon already has a velocity this side. And therefore, when this force acts, as I discussed in the third example, the moon is not going to go straight, but it is going to curve, isn't it? Imagine this is earth, and we saw that if an apple starts from rest, then it is going to go straight down, isn't it? And what if I throw the apple this way? What if I throw the apple this way? What if I give it some velocity this side? Then as we have seen, it will turn, right? Now it will fall this way. Now this is also falling, right? Isn't it? When you fall from your bed, do you fall this way? No, right? You fall this way. So if you call this one falling, then this is also falling towards earth, remember, right? Now try to understand one point. This apple was thrown by somebody standing here, right? Similarly, what if there was a person standing here and he throws the ball this way? Remember, for him this is horizontal, right? For him this is horizontal. So just like this apple fell this way, even this apple would fall this way, isn't it? And I hope you will agree that if a person standing here throws the ball this way, it will go this way. And a person standing here, if he throws the ball this way or the apple this way, it will fall this way, isn't it? Because the force is towards the center. So the force is not towards the center only here. The force is towards the center everywhere, right? Now, what if I throw this apple faster? Then it will fall further, right? If you throw it faster, it will fall further. What if I throw more faster? It will fall further. So do you see there is a chance that it may go and miss the surface of earth, right? So if you throw the apple with a proper velocity, there is a chance that it will not fall on the surface, but it will fall something like this. And once it reaches here, what this apple will do? Exactly what happened here, right? So it will go something like this. And once it reaches here, something like this will happen, right? It will curve this side. And when it reaches here, it will curve this side. So do you see, the apple is actually trying to fall towards earth, but it was thrown with such a high velocity that it did not hit the earth. It missed the surface of earth and started revolving around it, right? So exactly like that, even our moon is moving with that velocity, which makes it go in a circular path around earth. So the moon is actually falling, but it is falling from this straight line. So instead of going straight, it is falling this way, right? So the moon is falling, but it is falling away from this straight line towards earth, right? So just like the force of gravity was responsible for the moon to fall from this straight line and therefore revolve around earth, similarly the force of attraction on the electron by the nucleus is responsible for this electron to fall from this straight line, and therefore it also revolves around the nucleus. What if this force was not there? In other words, what if this nucleus was not there? Then, as you know, the electron would continue to move in the same straight line. isn't it? If there are no forces, then there will be no acceleration, and if there is no acceleration, the velocity will not change. So it will continue in the same direction without changing its velocity, right? Now what if somebody will ask you why this electron is not falling towards the nucleus even if it is getting attracted? Then the answer is very simple. The electron is not at rest. If the electron was at rest, then yes, it will fall straight towards the nucleus, just like this marker, right? If the marker is at rest, it will fall straight towards Earth. But if I give this marker a motion, I call it icha, okay, wish. So if I give this marker icha to go this side, and if there were no forces down, then it would have gone straight. It would have followed its icha. It's something like, you know, I give this example where you want to become a singer. Your icha is to become a singer. But here somebody is applying force, Pankaj sir maybe, who is saying no, you should be doctor. So you want to become singer. Pankaj sir says no, doctor, singer, doctor. Ultimately what happens? You become a singing doctor. So neither you go this way nor you go this way, but you go somewhere in the middle, right? So exactly for that reason, the electron is not falling because it already has a motion. So when you apply this force basically makes the electron turn. That's it. So is there any need to say that there is a centrifugal force in this direction which cancels the force by nucleus? There's no need to say. In fact, if you say there is a centrifugal force outward acting on the electron, there will be two questions for which there are no answers. Number one, if there is a force, then by whom? Who is applying this force? It is not the nucleus, because the nucleus is applying this force, electrostatic force. Then who is applying this force? Nobody, right? Because there is actually no centrifugal force only. Also, if this force cancels this force, then the net force will be 0. And if the net force is 0, then there will be no acceleration. No acceleration means velocity will not change, and therefore it will go in a straight line. So saying that this is there to balance this is not correct. Now let me tell you why there are some misconceptions where people say the centrifugal force balances the force by the nucleus. Why they say this? And that is because we write Newton's second law in a very wrong way. We write Newton's second law this way, isn't it? When we write this way, people start thinking that this is also a force which is acting on the body, because there is equal to. So people start thinking this also as a force which acts on a body. But please understand, this is not a force which acts on the body. This is the effect of force. Acceleration is the effect of the force. So the force is the cause and acceleration is the effect. That's why a better way to write Newton's second law is, if you apply force on a body, now that force could be due to nucleus, that force could be due to earth, that force could be due to Pankaj sir pushing something. So if you apply some force on a body, then the body will respond to that force by changing its velocity. Therefore, we should write the Newton's second law as the acceleration produced in the body is equal to force divided by mass. So this is a proper way to write, because this tells you that when you apply some force, the body accelerates, and the more mass you have, the less you will have acceleration, and the less mass you have, the more you will have acceleration. So this is the best way to interpret Newton's second law. Now I know if you cross multiply, you get the same thing. So I don't mind if you use this way, but you should not think MA as one of the force acting on the body. The force acting on the body has to be found from another source. For example, if the force is due to gravity, then the force is given by the formula G m1 m2 by r square. Similarly, if the force is because of charges, then we write the formula as 1 by 4 pi epsilon naught q1 q2 by r square. And if the force is due to spring, we write the formula as k times x. And the force is due to friction, then we have the formula as mu into n. So we have to discover the laws that gives you force. once you know the laws that gives you the force, then Newton's second law is not recipe to find the force. Newton's second law is recipe to find the acceleration. Why? Because once you get the acceleration, then you can find displacement using this formula, right? S equal to ut plus half at square. You can find the final velocity v equal to u plus at. So once you know where will the body be, once you know displacement, you will come to know where the body will be after time t. You will come to know what will be its final velocity. In other words, you will come to know the whole future of the body, provided you know the acceleration. And who gives you acceleration? Newton's second law. But for that, you have to find force through other laws, right? When you study the theory of atoms, you will see this equation. This is the force given by Coulomb. It is called the electrostatic force between the charges of electron and the charge of nucleus. And that equals to this quantity. Now, the problem happens when you consider this also as a force. So sometimes what people do, they think this is the electrostatic force, as you can see here, and they consider this as the centrifugal force. And they say the two forces are balanced. First of all, try to understand there is only one force acting on the electron. There is only one force by the nucleus. And if the forces were balanced, it will not turn. If forces were balanced, it will go straight. So therefore, this force does not balance this force because this is not a force. This is actually ma. So this is the only force acting, F. This is m. And this v square by r is what we call centripetal acceleration. All the students who have completed their class 11, they know that this is the formula for centripetal acceleration. Therefore, this is just direct application of F equal to ma. And that centripetal acceleration is provided by some force, right? According to Newton's second law, acceleration is the effect of a force. Now that force is provided by the nucleus. Now let me tell you under what condition it is okay to say electrostatic force is balanced by centrifugal force. Well, if you observe this electron sitting on top of this electron itself, then only in this frame of reference, because this person is moving with the electron will appear to be at rest, isn't it? Even if I may be running, for me my nose will be always at rest, right? I will not see my nose running somewhere, isn't it? So for this person, this electron will be at rest. However, there is a force from the nucleus. So only for this person to understand why this electron is at rest, he has to assume a force which acts outward, and that force is what we call as centrifugal force, and that is a pseudo force. It is a pseudo force. By pseudo we mean false. So it does not actually act on the body. It appears to act for observers who themselves are accelerating. So such frame of references where there is acceleration, we call them non-inertial frame of reference. In only such frames, you need centrifugal force to understand why the electron is at rest. Only in that frame of reference. But normally when you study atoms, you are not sitting on the electron, right? You are somewhere outside and you are thinking about the motion of electron. So in such cases, you do not need centrifugal force. Finally, I would like to show you a demo which is done by one of my students named Neha. So in that demo, she has taken some water in a bucket, and you all know if you invert the bucket at rest, the water will come down. So if you keep the water at rest, gravity will make the water come down. But if you give the bucket a velocity, a icha, a motion, then this gravity will not bring it straight down. What it will do? It will make the body turn. So you will see the water going in a circular path instead of falling down. So please have a watch.